Now let us see something where the compartments have sealing vents. Normally vents are provided in side walls where it can be in a form of window or a door, etc. But in some cases ceiling vents can be provided, which are openings in the ceiling through which the smoke can go out. Okay, the flow basically, if you see a compartment fire, the smoke goes up, hits the ceiling, there is no opening in the ceiling, so it actually spreads as a ceiling jet, then descends down, finds a vent opening and goes out. But if there is a opening in the ceiling, then the vent flow, the fire induced vent flow can be quite different, correct, when there is a ceiling vent, because already the flow is rising up, and if it finds a vent in the ceiling itself, then the nature of flow and the fire development in the compartment temperature, heat release rate, etc. will be quite different. Okay, so that is important. So for the vertically vented fires, that is where the smoke can leave through the ceiling itself through the vents provided in that, we can have, for wall vents, stratified two-way flows exist. There are two things. For fires in a vertically vented enclosures, wall vents, doors and windows, correct, and stratified two-way flow will exist. Okay, now for a single vent located in the ceiling, interesting flow patterns can emerge. Now, if the delta P, that is delta P is always the compartment pressure and the ambient pressure in this case. So, delta P here is greater than 0, that means the flow goes up. If the delta P, this is P ambient and this is P gas in the enclosure. Okay, now here in this case P G minus PA is greater than 0. Now, if you go to this case where this is PG and this is PA and PG minus PA is less than 0, then the flow comes in. But if the delta P is close to 0, then there can be a recirculation type of pattern. So, interesting flow patterns can emerge with a single vent provided in the ceiling. So, these are some special cases where the ceiling vents are also available. So, now compartments with ceiling vents, three conditions are typically observed. First one is choked flow followed by fire extinguishment, that the fire can extinct. Then second one is, that is what happens is, due to this pulsating type of or this different type of flow patterns which are created, the air entertainment can be affected. So, choked flow can occur and the fire can be put off, fire can extinguish. Then erratic pulsating flow or pulsing can also be observed. These are called ghosting flames. Okay, because of the flow pattern. As I told you, when the delta T tends to 0 at the ceiling vent, then the flow pattern becomes somewhat pulsating, and that will cause a lot of fluctuations in the flames, and such flames are called ghosting flames. In some cases, we can also get a strong steady burning because of the proper venting. When the proper venting takes place, then proper air entrainment also occurs. So, the fire continues to burn almost in a steady manner. Emmons and Cooper analyzed the airflow through ceiling vent using the concept of what is called flooding pressure. Flooding pressure, delta Fp, that is the flooding pressure in the form of delta P, is written as 0.0873 del rho square GD by CD square rho F, where rho F is the density of the air. calculate the compartment temperature T or Tg you can say. Then D basically is 4A by L, where this is like a hydraulic diameter. L is the perimeter, AV is the vent area. So 4A by P like that. So L is the perimeter here. And we can see that CD is calculated as a function of Reynolds number 0.138 plus 1.12 into 10 power minus 4 RE. So from the value of delta PF, flow patterns can be determined. If it is positive, that is compartment pressure, fluid pressure, compartment greater than fluid pressure, then the flow goes out to the ceiling vent or it comes down, or if it is close to 0, then you have a different type of flow conditions. So in compartment fires, due to the enclosure effects, several types of behaviors are observed. So this behavior differ when there is a growing fire and before the flashover occurrence, and after flashover it goes to a fully developed fire. There the situation is different and so on. And all this depends upon the venting conditions. And furthermore, if you have a ceiling vent, the situation will be entirely different, and we have different types of conditions like a choke flow or flame extinction, then erratic pulsation or ghosting flames, or a strong steady burning. Okay, that finishes this module. We will see some case studies where a fire in an enclosure is involved. The first one is an experiment conducted in Worcester Polytechnic Institute in USA. That's a very famous fire protection engineering lab. There a compartment as per the standard has been created. Some commodities have been kept and it is set to fire, and how the fire is developing there has been shown. The stages of fire has been shown here. Then the second case is done using a software called fire dynamic simulator. Here the enclosure fire sourced by a liquid fuel methanol pool is used, where it is clearly shown that after the fire develops, how the flow goes out of the compartment and the air comes into the compartment, etc. And the smoke layer height also is shown as a function of time. The third one is the fire set over some series of wood crypts which are kept, and how the fire actually initiates, tries to spread over the wood crypt, and how the adjacent wood crypts are ignited by the hot smoke layer descending down, etc. is shown. So we will see about the characteristics of these three fires. First one, as I told you, is the fire which is done in a model compartment in WPI. It is Worcester Polytechnic Institute in USA. It is near Boston. So here you can see the commodities in the room. So there is a couch, there is a dustbin which is actually set to fire, there is a computer table, and there is a chair, and there is a cupboard, etc. And you can see that there is some lighting also which is there. So electrical fire also is possible. And how these commodities catch fire? Typically a room which is made up of materials used in the dormitories of a college. So that is what is used here. So now this video starts with see, for example, I have the initial fire occurs in the dustbin here, then it grows, and you can see that due to the fire goes up and some particles are falling over the couch. You can see that some localized ignition happening at the couch. It is not, it is like, see, you can also see that the fabrics, I will just see here. Here you can see that the couch is not burning entirely. There are some fire particles which are thrown out, and it is igniting the lateral part of the couch and also the sitting seat here, and the fire is slowly developing. Till now we can see nothing is happening to this computer table. So far the fire is basically oriented towards the fabrics which are easily ignitable, and now we can see that slowly the table is also catching fire, and the fire is growing at a strong rate. And if you see the smoke layer now was grey. Previously the WPY, that symbol was appearing. Now we can see we are not able to read that. That means the smoke has intensified here, and now we can see that the fire is spreading at a violent rate because of a huge mass of ignited materials. You can also see that there are some paper materials. Now couch is fully under fire, and the shoe etc. is also burning. Now the table is completely ignited. One part of the table is completely ignited, and the burning nature of the fabric is such that it actually flows some burning particles over the room, and it falls over the other commodities. So you can see that here, since this fire is oriented towards the wall, you can see the wall effect here. So you can see a dark smoke coming out of the wall and a smoke layer going up, and you can see the descent of the smoke in this area, the descent of the smoke in a proper this direction there. And here now entire smoke layer is descending here, and you can see that some commodities are burning and the smoke layer is oscillating, and now the temperature of the smoke is slowly increasing. Now you can see other commodities are burning. Now this couch is, this chair is also paralyzed, not ignited till now, but it is paralyzed, and now we can see that nothing is visible. The visibility has totally decreased, and you can see this, the smoke layer has descended to this part, that nothing is visible now. If you just try to zoom out, you can see that fire flashover has occurred at this point. At this point in time, flashover has occurred, where it is very clear that all the commodities are ignited suddenly. Okay. So now in the flashover situation, you will see that the fires are coming out of the compartment because of the fact that more fuel is generated and it needs more air to burn. Okay. Let us see the important stages of this fire again. So when it is ignited, you can see that the part throws some balls, some fire particles to the lateral portion of this, and you can see this is also catching fire here. You can see this. Then what happens is slowly the fire is spreading, growing now. Now the WPA is visible here. The visibility now this smoke is grey, not becoming dark, and you can see that the couch, which is easily made of fabric material, is easily ignitable, and it ignites and it burns now. Now it burns at a faster rate, and now the smoke layer is going up towards the side wall. You can see here towards the side wall, you can see that there is lot of activity. That is, the smoke actually forms, and it grows from this because of the fact that there is no enough oxygen. Here you can see that it is more luminous burning, but here towards this side where the oxygen is stored, there is some formation of smoke. So now you can see the visibility slowly reduces. The smoke accumulates on the top and tries to come down as the burning continues, and you can see that now in this wall region more smoke is generated, and the fire now engulfs over the entire couch. But till now you can see the other commodities are safe, they are not ignited at all. Now going through this, the fire basically becomes more and more violent, and entire couch is now burning. The heat release rate is increasing, the smoke layer has become more and more darker, temperature of the smoke layer has increased to a good value. Now you can see that this fabric burning throws up materials. You can see the particles throwing up and falling on the other commodities. Okay, that is how the later part of the couch was ignited. When from the fire, these are particles are falling due to the fabric burning, because the loose particles are carried away, the burning particles are thrown to other commodities also. But this is not enough to ignite these commodities. You can see this. And now you can see that the violent fire, the smoke generation near the walls, accumulation of the smoke, oscillation here you can see, entire coach is vigorously burning. Now the smoke layer descends. At this point you can see this, the keyboard, the computer table is now ignited. Still the chair and other commodities are not ignited. The chair has slowly started to pyrolyze, but ignition has not occurred. Now if you continue this, the smoke layer descends and temperature of smoke increases. Suddenly at one particular point, you will see that the smoke layer now comes down and touches these commodities, but not able to ignite them till now. So the commodity, the fire has not set up to all these commodities till now. But as the smoke layer is descending and the temperature of the smoke layer is increasing, you will see that the visibility is totally lost and the smoke layer now comes in. Now we can see at this point rapid ignition occurs for all the commodities are ignited, and the smoke is trying to come out of the compartment room here. You can see this, all the commodities. This is the onset of flashover. The flashover actually occurs only when the temperature of the smoke has reached a particular value which can radiatively heat the commodities. So that means here in this case, here I will go to this particular point. Yeah, here this big fire is not able to ignite them. Only the smoke layer temperature, because of separation distance basically, after a particular point you can see that the ignition occurs because of the smoke becoming hotter and hotter. Okay. So flashover, one of the thumb rules what we saw was the smoke layer temperature reaching a delta T of 500 Kelvin plus. So that has caused this. Now after the flashover, you can see that the smoke or the fire itself comes out and burns because lot of fuel is generated, but air which is entering through this is not able to supply the oxygen. The fuel which are generated, gases are generated which is coming on burning. So this is one of the typical experiment. The second case study is on a simulated fire where you have a liquid pool where there is a steady burning. Steady burning is occurring, and the compartment dimensions are, the length of the compartment is 3.6, width is 2.8, length, width and height is 2.13, and we are showing the temperature colored as red highest and blue lowest, and there are two graphs which are shown. One is the heat release rate. You can see the heat release rate is steady, and layer height, that is the smoke layer height, as a function of time, which is also shown. The door or the vent, what we can say, has the dimensions of width 0.74 meter, height 1.83 and thickness 0.2. Here what we are trying to analyze is how so this is the opening, so this is the door, something which is open, correct. So here the smoke tries to go out in the upper part and air comes to enter in from the lower part, and there will be a formation of neutral plane in between these two where delta P equal to 0. So when I play this video, you can see that as the fire burns, air comes in from the bottom portion here. Air comes in the bottom portion, this, and gases are escaping, air is coming down like this, and actually entrainment is very severe because of this big opening, door opening, no. So entrainment is very severe, it actually pushes the fire towards the left side of the wall, and you can see the dynamics of the flow. Okay. In general, we see that the hot gases rising up, and also this pushing, creating some recirculation zones, etc., and lot of activities are there, turbulent activities. Then the flow rises up, hit the ceiling and goes as a ceiling jet, and once it descends down to a particular height, it tries to go out like this. So somewhere here the neutral plane should be there, above which the flow goes out and below which the air comes in. Okay, now continuing to play this, you can see that it is a steady fire. So but only thing is the fire is slightly tilted due to the good amount of air entering here. Now the smoke layer height varies. Initially it is higher, it is tend to descend down, then it becomes constant, because as the flow goes out, it becomes steady layer at about say 0.5 meters, maybe from the top. Okay, so measure from the top. So here the temperature of the gases is colored in the vectors itself. So for example, the blue color shows a lower temperature, about say we can say 150 degrees centigrade, something like that, and the hot the arrows with red colors etc. shows the higher temperatures. So here it is clear that for a steady fire and fully developed fire, we can see that the neutral flame is formed and the hot gases go out of the compartment to the top part, and the gas come in, and you can see the interaction. The sealing interaction is very clear, impinging, formation of jets etc. But as the flow goes, it also circulates like this. You can see this because of the corner effects. Because of the tilted flow, you can see that the flow goes, hits and comes down again. That means the product of combustion also is recirculated. That is the well stirred condition. When you see the recirculation zones etc. formed here, gives well mixed condition, which was the assumption we made, correct? Well mixed condition. That is, the compartment temperature is kept almost uniform because of this well mixed condition. So when I take a point here, I say temperature is Tg or density is rho g. That means the condition here, the gradient in this direction is not very much. That is fine, which is actually shown here because of the convection. The well mixed condition is reached. So that assumption can be valid. Okay, now you can see that the velocity values are very low here. Suddenly you can see that, and in this exit opening the velocity is high. So that assumption also, at the far field, recirculation zones etc. are there, the velocity value will be tending to 0, but at the exit plane you can see the velocity value will be finite. That is also here. Similarly, in the ambient side, velocity value here is 0, and here you can see the generation of velocity, and again towards the compartment it becomes 0 again. So the recirculation zones etc. is created. So the assumptions what was made in a simple analysis, what we have shown in the theory of somewhat uniform temperature, velocity is approaching 0 inside the compartment and outside the compartment etc. are signified here nicely. And here, as I told you, a neutral plane is also formed somewhere here, so that the below the neutral plane there is entrainment, above the neutral plane the thing goes out, and because of the opening extending to the ground, you can see a strong entrainment occurs and the fire itself is tilted towards the left corner. This is one of the scenario. So steady fully developed fire, we can have a scenario of a neutral plane formed automatically at some height from the vent bottom, where above that the flow goes out, below that the air comes in, and the well mixed condition is established by the recirculation zones which are created. Okay, so this is the scenario. You can see this recirculation zones etc. But basically the simulation gives some qualitative data of how the flow goes out, and it is velocity vectors colored by the temperature. Now the third case study, you can see that again it is an enclosure fire, but not in a room or anything. It is like a storage facility or something, where you have wooden wood grips like this stored at a given separation distance between these two. There is a given separation distance. Similarly, in this direction also there is a separation distance, and we will see that there is only one exit here where the flow can go out. There is some air which is there is in the compartment. The length of the compartment is very high, 25 meters, and the width is about 5.6 meter and height is 2.8 meters. Now this portion is ignited, and you can see the heat release rate after ignition increases sharply and goes to a maximum value. Okay, when I play this video, you can see that this is burning now. Smoke is formed, a plume is formed, but this plume is like a strong plume, because you can see this, the height is only 2.8 meters and the flame height is actually comparable to this, about half of the this. So HF is basically, we can say, equivalent. You can see that flame even touching the ceiling is equal to H. This is H, no? This is ceiling height. So here we are talking about something which is strong plume. Okay, I'll play it again. Yeah, you can see this. I'll pause this. You can see that the strong plume is generated because of a low ceiling in this particular case. As I told, strong plumes are very tough to estimate, experimentally evaluate, theoretically evaluate. So you can see this evidence here. As the ignition occurs, the smoke layer forms and searing jet forms, and searing jet clearly goes, because of the strength of the plume here, the searing jet is very powerful and it goes traveling about 25 meters and goes away to the vent, and the searing jet is basically very strong because of the strong plume. Why I am saying strong plume? Because you can see this, the flame which is formed here has height which is clearly very high. Yeah, you can see that the flame forms and the height grows. You can see the visible flame now. So slowly initiating, and you can see the visible flame now. Here the flame has extended to a height which is comparable to the ceiling itself. So a strong plume generates and it goes. Now the flame actually doesn't spread, only these three are ignited. The flame actually doesn't spread over the other crypts till now. Okay, what happens is basically the smoke layer becoming hotter and hotter descends down slowly, and at a particular point, I will just play it again. Yeah, at a particular point you can see that the smoke layer is formed, the searing jet is formed and it descends down. Okay, and now the flame actually grows over these three. So the established fire is there in these three things. Now the smoke layer descends down. You can see the smoke layer descending down. Now it will cause ignition, simultaneous ignition of all these grips. You please see that the flame which is established here does not spread over. The flame does not spread over these commodities. Still here only it is burning, but the smoke layer which has descended down has already heated up these crypts. So pyrolysis has already taken place here, which is not actually visible. So due to which what happens is, when I continue to run this, you can see that simultaneously all the crypts will be ignited, because the gases are available. Once the gases mix with temperature, mix with the, I will just go to that point. Yeah. Once the gas reach C, you can hear C. Once the pyrolysis is also happening, because of the radiation from the smoke layer, pyrolysis has occurred to the all the grips here. So pyrolysis gases are there in the smoke layer along with some air. So once the auto ignition temperature is reached, immediately all the grips are burning at a faster rate, and it is not a flame spread over this consecutive or subsequent grips. It is a simultaneous burning of all the grips due to the sealing jet which is actually heating up the grips. So if you see it again, you can see that all the grips are burnt at a very faster rate. So if I play it again, you will understand that. Yeah. So now please understand that why this last grip is burning for a longer time. These intermediate grips are not actually fully burnt, because now when once the flame pyrolysis has occurred from all these grips, the fuel vapors or fuel gases would have gone to the smoke layer, and this air which is already there, which has come in due to the entraining of the ambient air would have caused the premix thing to burn here, but still the entire wood crisps in the between in these layers have not fully burnt. But if you see, the last crisp is burning because now it receives oxygen from the ambient and it is burning for some longer duration. Okay, so you can see the video one more time. All the crisps are ignited, then this all the first 3 sets is now fully ignited and the steady flame forms, and the smoke layer as a sealing jet goes out and descends, becomes hotter and hotter due to the strong plume, and this hot smoke layer pyrolyzes these crisps, and you can see the pyrolysis vapor will be coming out, and now the flame spreads as a premix flame, correct, over entire this, but these intermediate crisps are not fully burnt because of the fact that no oxygen has come in now. The last set of crisp is now burning because of oxygen coming down, and this is burning for few more time. Do you understand? Because oxygen is available only for this crisp now. Okay, the pyrolysis gases has allowed the flame to propagate as a premixed gases to the last crisp, and last crisp receiving the oxygen burns for longer time. So this is the situation. So lot of features are available in the compartment fires, especially when you have enclosures which are going to confine the fire and allow some distractions or some constraints in the air entrainment. Okay, so these are the 3 case studies. I'll stop this. We'll go to the next module in the next class.